Bismillahirrahmanirrahim. In the previous lesson, we looked at the acidity of the different types of carboxylic acid. It all depends on the electron donating or electron withdrawing effect. Okay. We also looked at the reactions of carboxylic acids, how it behaves like an acid in a reaction where it can react with metals, alkalis, and carbonates. Okay. And then we looked at the oxidation of alcohol in your AS syllabus. Okay, primary alcohol can be oxidized to aldehyde first and then only to carboxylic acid. Okay, and then in your AS syllabus, we said that it stops there at carboxylic acid. Okay, no further reaction can happen. But actually in A2, you will learn that certain carboxylic acids, specifically for your syllabus, it's the methanoic acid and the diethanoic acid, can be oxidized further. Okay, so that is something that it's new for you to learn. Okay? So recognize that some carboxylic acids can be further oxidized using an oxidizing agent, of course. Okay. So if methanoic acid is being oxidized, that makes methanoic acid a reducing agent. Okay. Right. I'll talk about that again in the next slides. Right. So carboxylic acids cannot usually be oxidized further except for methanoic acid and ethandioic acid. Okay, ethandioic acid, I will show you the structure. It's when you have 2 carboxylic acid and only 2 carbon because it's ethane. So it would look like this. Okay, but you will have this drawing in your notes, I hope. In the next part, I think, not on this page. Yeah, we'll have a look at that later on. Okay, so what happens when methanoic acid is oxidized? So this is the structure of methanoic acid. Now, the equation looks a bit different on my slide, okay? But when I hope you can understand, you know, there's some overlap here if you notice, okay? So you are asked to draw the equation. Okay, let's have a look first before we start drawing. So what is the oxidizing agent that we can use to oxidize methanoic acid further? Okay, we're going to use a mild oxidizing agent. You've met this reagents already, but you probably wouldn't see it as an oxidizing agent, a mild one. It's called the Fehling's or the Tollens reagent. Okay, I hope this is familiar. These are the reagents you use to test for aldehyde. Okay, so that means what happens? Why do we use Fehling's and Tollens reagent? If you look at this part, aldehyde will be oxidized further. Okay, so Fehling's and Tollens is actually an oxidizing agent. You see this square bracket O. So that oxidizing agent, Fehling's reaction or Tollens reagent, is an oxidizing agent where it can oxidizes aldehyde. But only for aldehyde. Ketones will not react with Fehling's and Tollens. Okay. So what do you have to do? You just have to warm it or heat it. And then there will be some observation that you would observe, which I will talk about later on. So what happens during this oxidation process? Your methanoic acid will react with an oxidizing agent, which is you can either choose Fehling's or Tollens depending on which one is available. But in the equation, you only have to write down square bracket O. Okay, so this is the full equation. It will be oxidized into carbon dioxide, CO2, plus water, H2O. Okay, so can you fill in this equation under full equation? Okay, on your notes on page 3, where it says full equation, okay? And then the half equation for oxidation will be, oh yeah, okay. So this is the full equation. You can either draw it out as a full displayed formula, or you can just write it down as molecular formula or structural formula, okay? Make sure that when you're asked to write down the equation, you balance it, okay? How to balance the equation? You count the oxidizing agent as an oxygen, okay? If you need 2 oxygen, then you will multiply this by 2. If you need 4, you multiply it by 4, okay? The reason why we use a square bracket always easy for you to balance the equation. You don't have to write down failings. In the case of failings, it's actually Cu2 plus, or in the case of tollens, it's actually silver, okay? So you don't have to worry about balancing those equations. Now, failings and tollens is a less commonly used oxidizing agent. We only use it, so far, we only use it to test for aldehydes, okay? But now you know that it can be used to oxidize your methanoic acid further, okay? But of course, you can use a much stronger oxidizing agent, which is the common one, the commonly used, the acidified potassium manganate or acidified potassium dichromate, okay? No problem. This should also work with either mild or strong oxidizing agent, okay? The half equation is, cannot really see it, okay? So I'll write it down. The half equation for the oxidation of methanoic acid is HCOOH, OOH to be oxidized into CO2 plus 2H plus 2E minus, okay? So the oxidation number of the carbon in the HCOOH is +2, and then in the CO2 it's +4, okay? So that's why you see an oxidation for methanoic acid. Okay, if methanoic acid is being oxidized, that makes it a reducing agent. Okay, so reducing agent. Methanoic acid is actually a strong reducing agent. That's why it can be oxidized. Okay, if it's not a strong reducing agent, then it cannot react further. It cannot be oxidized further. If it reduces another species, itself will be oxidized. Okay, remember they always have the opposite effect. Right, moving on. I hope you have done copying this down. Next, so this is the observation that we are supposed to see when we use the Fehling's reagent, okay? So Fehling's reagent contains Cu2 plus in a solution, okay? What happens is the Cu2 plus in Fehling's reagent will be reduced to Cu plus ion, okay? Because Fehling oxidizes methanoic acid. Fehling itself will be reduced, okay? So you go from Cu2 plus to Cu plus, and you will observe a brick red precipitate, okay? The brick red precipitate is actually the color of your Cu plus. So it will be exactly the same positive observation for aldehydes as well, because you're using the same reagent, okay? The next one is, I think my slides is being cut off here. The next one is if you use a Tollens reagent. Tollens reagent contains silver ion, okay? Silver ion will be reduced to silver metal, silver solid. That's why you see a silver mirror. Usually we say silver mirror, okay? So silver mirror or silver metal will be observed. And this shows that an oxidation reaction has happened, okay? So when you see a silver mirror with Tollens reagent or a brick red precipitate with Fehling's reagent, now you know that it can be aldehyde or methanoic acid. Okay, in AS you will only know it as or phthalings and toluenes will only be positive for aldehydes, okay? But when the question comes in A2, you need to remember it's aldehyde and methanoic acid, okay? So if there is a reduction happening in your phthalate, that means oxidation must have occurred in methanoic acid, or oxidation must have occurred in aldehydes. Okay, same thing as your toluenes reagent. Toluenes reagent will be reduced from Ag plus to Ag metal. So there's a reduction happening. The methanoic acid must have been oxidized already. Okay. The next type of carboxylic acid that can be further oxidized is ethandioic acid. Okay, so this is the structure where you have 2 carbon and 2 carboxylic acid group, COOH. Okay, so ethandioic acid is a dicarboxylic acid. The di means you have 2 functional groups of COOH. It can be oxidized by a much stronger oxidizing agent. Okay, it doesn't work with phthalings and toluenes. So this is something that you have to remember. For ethandioic acid, it can only be oxidized by a much stronger oxidizing agent, which is, as you know, acidified potassium manganate or acidified potassium dichromate, and then you warm or heat it. Okay, this doesn't work with toluenes and phthalings reagent because toluenes and phthalate is much milder oxidizing reagent, and ethandioic acid is not as strong as a methanoic acid as a reducing agent. Okay, the product will be the same. You will get carbon dioxide and water. Okay, so what happens here is that a solution of ethandioic acid can be used in titration. Okay, the reason why we can use in titration is because potassium manganate. I don't know if you remember carrying out a titration with potassium manganate. Okay, it's easy to carry out a titration with potassium manganate because you don't need an indicator. Okay, potassium manganate is already what do you call this? Self-indicating. Okay, it starts with purple, and then it will be reduced to Mn2+, which is colorless. Okay, so the word standardized means here is to work out concentration. Okay, standardization means to, oh yeah, it's here, to work out the exact concentration of an unknown solution. Okay, if I say I want to standardize this solution, that means I want to find out the concentration of an unknown solution, of this unknown solution. Okay, the usual, you will carry out the usual titration procedure. So how is the procedure? This is important, especially for paper 5. Actually, in paper 2, they can also ask you how would you use this experiment to I don't know, investigate or to work out the concentration of the unknown reagent. Okay, so what you can do is you dissolve the ethandioic acid first. Okay, ethandioic acid comes in a form of solid. You dissolve it in water to make it aqueous. You weigh it out. Okay, so if you know the mass of the ethandioic acid, you know the volume of water that you make, you know the concentration of the ethandioic acid. Okay, so in this case, your ethandioic acid is your known concentration. Okay, that means your other reagent is the unknown one. So you make a standard solution. Okay, standard solution means you know the concentration of that solution, right? You want to react the ethandioic acid with the potassium manganate. Potassium manganate is the unknown solution. Okay, if you know the number of moles of ethandioic acid, you can find the number of moles of the potassium manganate solution because you can work it out by mole ratio. Okay, so what are they saying here? The potassium manganate solution is to be standardized is then run into the titration flask from a burette. Okay, so if I draw this out, the reason why I draw this out is because so you know the color change. Okay, so you need to know when identifying the color change, you need to know who is in which instrument, okay? Who is in the flask, who is in the burette, okay? From this statement, it says potassium manganate is then running to the toilet from a burette, okay? So potassium manganate is in the burette, and you have your ethandioic acid, CO2H, HO2, okay, is in the flask. And you know that ethandioic acid is colorless, and the potassium manganate is purple, okay? So the color change, right, this is extremely important. When the question asks you for the color change, you have to look at the color change in the conical flask, not the color change of the potassium manganate, not anything else. It has to be the color change inside the flask, because when you do your titration, you're looking at the conical flask, right? Not the burette, not the pipette, not elsewhere, okay? So what happens is that the color change would be from colorless to first permanent pink, okay? So first permanent pale pink. You don't want to see purple. If you have purple, that means you're already in excess, okay? So I think the statement here, at the end point, well, all the ethandioic acid has been oxidized, a drop of purple, I cannot see, a drop of purple manganate solution turns the solution pink, okay? So the moment you see pink in your conical flask, you stop. Do not wait for it to go to purple, because I know potassium manganate is purple, but when you do a titration, you don't want it to go in excess, okay? The first color change that you see is the endpoint, the first permanent pale pink color, okay? Not even dark pink. So the color change that you would see here would be colorless to purple, okay? Not purple to colorless. You don't look at the color change of the potassium manganate. It has to be the one in the beaker. Sorry, the one in the conical flask, okay? And then you are asked to write down the half equations, okay? So the half equations, you would need half equation for oxidation and half equation for reduction, okay? So for oxidation, obviously it's the ethandioic acid being oxidized, and then for the reduction, it is the manganate ion, okay? So you need to be familiar with these half equations, which you already have learned in AS. Now you may be wondering, my oxidizing agent is acidified potassium manganate, H plus KMnO4, okay? But remember, the element that is being reduced is the manganese, the Mn. So you can ignore everything else. You can ignore the H plus. Well, the H plus is there because it's needed for balancing of the equation. You can ignore the K plus, okay? Why do you not include K plus? Because you only want to see the species that is being reduced, Mn, okay? But Mn doesn't exist as Mn on its own. Okay, the Mn has to be in MnO4 minus. Okay, so half equation for MnO4 minus can be found in the data booklet, so you don't have to worry about that. It's just this one. Okay, don't get confused. It should be written as COOH2 to be oxidized into carbon dioxide plus 2H plus 2 electrons, okay? So my PowerPoint slides appear differently when I move it to my iPad, okay? So it should be in a single line like that, okay? Don't get confused with the 2 electrons. It should be on the product side. For reduction, well, I will not say much on the reduction bit, okay? Then, after they ask you to write down the half equations, obviously they will then ask you to write down the full equation, okay? The full equation is when you combine 2 half equations together. So that's oxidation plus reduction, okay? But before you combine these two, there's one thing that you need to remember. the electrons need to be balanced. Okay, so in oxidation, you release 2 electrons. In reduction, you are using up 5 electrons, so they don't match. Okay, so what you have to do is you have to match them, right? So this oxidation equation, you multiply it by 5, everything multiplied by 5, and then the reduction half equation, you multiply it by 2, so that you get 10 electrons on each of the half equation. Okay, so you don't just multiply the electrons, you have to multiply every single thing. And then of course you combine them and tidy them up. Okay, I hope you know this already. What I mean by tidying it up is if you have H plus on both sides, you will have to simplify them. Okay, so it turns out that after simplifying, this is what you get: 2MnO4 minus plus 6H plus 5 COOH2, that's your diethanoic acid, plus 2Mn2 plus 10 CO2 plus 8 H2O, I think. Yeah, 8 H2O. Okay, so please write down this equation correctly. Maybe I'll rewrite it for you just in case you don't get it. Okay, 5 COOH2 to form 2Mn2 plus 10 CO2 plus 8 H2O. Okay, so that's the full equation. The next part is basically oh no, I've not mentioned this next part yet. So the manganese ions form can catalyze the reaction. This is an example of an autocatalysis. One of the products in the reaction act as a catalyst for the same reaction. Okay, so basically, initially at the start of the reaction, when the reaction hasn't started yet, the reaction will be very slow. Okay, this reaction, the oxidation of the oxidation of diethanoic acid by manganate is actually catalyzed by Mn2+, which is the product. Okay, the moment you produce Mn2+, then the reaction speeds up. Okay, so this is what we call autocatalyst. That means that reaction is producing their own catalyst. Okay, automatic. You don't have to add external catalyst. Okay, you don't have to add Mn2+. Why? Because you will form Mn2+ in the reaction anyway. So initially your reaction will be slow. The moment you form Mn2+, then your reaction will start to speed up. Okay, this is what autocatalyst means. The products in the reaction act as a catalyst for that same reaction. Okay, so if you look here, this reaction is catalyzed by Mn2+, which is the product. Okay, moving on. Yep, I've already talked about that. Okay, so why is methanoic acid never prepared by refluxing methanol with acidified potassium dichromate? Okay, so basically they're saying when we can actually react methanol, which is C, I'll draw it out. CH3OH, okay, with acidified potassium dichromate. Now, acidified potassium dichromate is an oxidizing agent, okay? When we oxidize our methanol, it will first be a methanon, okay? And then it will be oxidized further into methanoic acid. Okay, in AS, you would think that the reaction stop here. Methanoic acid is the final product. But actually, A2 taught you that methanoic acid can be oxidized further into CO2 plus H2O. Okay, so that's why we cannot use methanol to produce methanoic acid, because the reaction will be continuous. Methanoic acid will be further oxidized into carbon dioxide and water. Okay, so that's the reason. The next question, in a titration between ethandioic acid with potassium manganate, suggests why the solution of ethandioic acid is heated before adding potassium manganate. Okay, so usually when you need to heat a reaction or you need to supply light to a reaction, this is because the reaction is slow. That's it. You just need extra energy to overcome the activation energy. Okay, so basically we heat it because we want to speed up the reaction. Speed up the reaction. Okay, because initially the reaction will be slow until you produce Mn2 plus, then only your reaction speeds up. Okay, so this brings us back to autocatalysis. Okay, so the heating is just for the starting, the first part. Before you produce any Mn2 plus, your reaction will be very slow. The moment you produce Mn2 plus, then your reaction will start to speed up because Mn2 plus is the catalyst. And if you look back at your equation, Mn2 plus is actually your product. Okay. Right, so that's the reaction of carboxylic acid, the oxidation of carboxylic acids. Only 2 carboxylic acids can be oxidized. The next section, I don't think we will have enough time. We might have, okay? So the next section, which falls under carboxylic acid, is acyl chloride, okay? So acyl chloride is a derivative of an carboxylic acid. That means it comes from carboxylic acid. So if I just write down R, which stands for any alkyl group, it can be H, it can be methyl, it can be ethyl, propyl, and etc. So this is my carboxylic acid. Okay, acyl chloride is when I have the OH replaced with chlorine. Okay, so this is what acyl chloride is. Acyl, if you remember from topic 15, benzene, the Friedel-Crafts acylation, okay? An acyl group is an alkyl with a carbonyl group, okay? Alkyl plus carbonyl. Carbonyl is C double bond O. Carbonyl. Okay, so this green part is your acyl group. Alkyl plus carbonyl. Acyl, okay? And then the chloride is self-explanatory because you have a chlorine hanging on the carbonyl carbon, C double bond O, okay? Right, so the functional group of an acyl is the C double bond O Cl. Okay, acyl chloride can be prepared by the use of carboxylic acid and Socyl2 as OCl2, PCl5 or PCl3. Okay, you've come across this reagents when you want to change your alcohols into haloalkanes. Okay, obviously you can see that this reagent contains chlorine, so that is like a supplier of chlorine. Okay, so to make an acyl chloride, obviously it has to start from the corresponding carboxylic acid. Okay, because as you can see, the acyl chloride looks similar to carboxylic acid. The only thing that's different is the chlorine instead of having an OH. Okay, naming, you have to count the number of carbon. So if you look at the carbon here, 1, 2. So you have 2 carbon, so you call it ethanoyl chloride. Okay, if you have 3 carbon, it will be propanoyl chloride, butanoyl chloride, and etc. Okay. Describe the reactions of carboxylic acids in the formation of acyl chlorides. Okay, so I will go through this quickly. Just now, I have mentioned the 3 reagents that you can use. You can use Socyl2, PCl5, or PCl3. Okay, these different reagents will require different conditions, right? So for example, if you want to form an ethanoyl chloride, okay, obviously you have to start with an ethanoic acid. Okay, if you look at the structure, do you have to draw this? Okay, you have the equation in your notes already, but if you want to draw out the structure, you can, as shown on my slides. So if you want to produce an acyl chloride with 2 carbon, obviously you have to start with a carboxylic acid with 2 carbon as well. Okay, so what happens is you are replacing the OH with chlorine. Easy. Okay, this is an example when we use phosphorus chloride, PCl5. For PCl5, no special condition is needed. You just have to add PCl5, let it react at room temperature. Okay, so you will get ethanoic acid to be converted to ethanoyl chloride, and then you will get other product like POCl3. So that's your phosphorus compound, and you get a hydrogen chloride gas. So this appears as steamy fume, so that must be a gas. Okay, PCl5, if I'm not mistaken, is a solid at room temperature. Okay, so PCl5 is a solid, and ethanoic acid, as you know, is a liquid at room temperature. Okay, so steamy fumes, it's something that you can observe. So this can be used as a test. Okay, as a matter of fact, this reaction is also used as a test for alcohol. So now you know alcohol and carboxylic acid can react with PCl5. How do you observe? You will see steamy fume, or sometimes they say white fumes. Okay, so that steamy fume is your hydrogen chloride gas. Sorry, did I say hydrochloric? Hydrogen chloride gas. Okay, it's not an acid, it's not a liquid, and for this reaction, you do not need a special condition. So that means you just simply throw in PCl5 into your carboxylic acid. Okay, the second type of reaction is if you use PCl3. Oops. PCl3 requires a special condition. Why? You don't have to know that, but just remember it, okay? PCl3, you need to heat it up. And same thing, if you want to produce an ethanoyl chloride with 2 carbon, you will use an ethanoic acid, okay? So you will produce a phosphorus acid, okay? So you don't see steam this time. PCl3 is a liquid. Ethanoic acid is a liquid. Okay, so this will most likely be a liquid as well. So it's a phosphorus acid. Phosphorus acid. Okay. Well, I didn't draw the structure, but it will be more or less the same like this as well. Okay, the other product that you will form is just H2PO3. You have to remember the equations when asked. Okay, and it has to balance as well. So using PCl5 will give you different products. Using PCl3 will again give you different products, okay? But it will give you the same ethanoyl chloride. If I were you, if I were given an option to choose between PCl5 and PCl3, I would use PCl5 because I don't have to heat it up, okay? With PCl5, with PCl3, you have to heat my reaction. Okay, the last one is SOCL2, SOCl2, which is sulfur dichloride oxide. Same thing. If you want to form an ethanoyl chloride, you will use ethanoic acid, okay? SOCL2 will give you a different product from PCl5 and PCl3. You will get a sulfur dioxide gas, okay, and a hydrogen chloride gas as well, okay? SOCL2 is liquid at room temperature, and the carboxylic acid is liquid at room temperature, okay? So for SOCL2, no special conditions needed. So that means you don't need to heat it up. It can happen at room temperature. Okay, so these 3 reactions, as you can see, these 3 reagents will give you the same acyl chloride, but the side products are different. Okay, and 2 out of 3 reagents do not need special conditions. You can use PCl5 and SOCl2 straight away, throw it into the carboxylic acid. Okay, only with PCl3 that you require, you need to heat it, you need to warm it, right? So right, I think we will stop there. You can try question 4.1 first. Okay, write a balance equation using the structural formula for the formation of propanoyl chloride. Okay, so the tip here is, if you want to form propanoyl chloride, then you would need a propanoic acid. Okay, the number of carbon atoms that you want to produce in your acyl chloride has to be the same number of carbon atoms you have in the starting material, which is your carboxylic acid. So if you want to form propanoyl chloride, you will need to use propanoic acid. Okay, and then different reagent will give you different product. Like SOCl2 will give you SO2 and HCl. PCl3 will give you other things, and so PCl5. Okay, so I will stop here because we have less than a minute left. If you have any questions, please ask in the group. Just to let you know that Monday is a public holiday, so there will be no lesson. Okay, right. Assalamualaikum warahmatullahi wabarakatuh. Thank you, everyone.
Thank you, Miss.
You're welcome.
Salam. Thank you, Miss.
Thank you, Miss.
Bye.